Bismillahirrahmanirrahim. Okay, today we'll begin our new lecture on the introduction to bridge engineering. But if you have any questions in the previous lectures, you can ask your questions, please. Any questions in the previous lectures? Okay, if there are no questions, then let's begin our lecture on the introduction to bridge engineering. Topics included in today's lecture are introduction, then bridge components, types of bridges, loads for bridge design, and one complete example on the analysis and design of simply supported RC bridge, famous bridges in the world at the end. The objectives of the lecture are that students will be able to differentiate between a bridge and a culvert and explain how different types of bridges resist loads and analyze and design simply supported RC slab bridges. Okay, first of all, we will define a bridge. What is a bridge? Bridge is a structure having an opening not less than 6 meters or 6,000 millimeters that forms part of a highway or over or under which the highway passes. Part of a highway means that they are at the same level. Over means that highway, the bridge is over the highway, and under means that it is an underpass. So in all the three cases, it will be called as bridge. And then the difference between a bridge and a culvert, the definition is although not very clear and defined in many books. However, for the purpose of terminology, we will call those structures as culvert whose total overall span is less than 6 millimeter or 6,000 millimeter. So any opening with less than 6 meter, and then if it becomes part of a highway, then it will be called as culvert. Then structurally, there are many types of culverts, box culverts, like you can see in the figure in the middle. And the figure on the right, you can also see a multi-cell culvert, a multi-cell culvert and a unicell culvert. And there can be many other types of culverts depending on the span, depending on the structure, depending on the material. On the left, you can see a bridge, which is basically an arch bridge, truss arch bridge. Okay. You know that bridge is one of the key elements in a transportation system because it controls the capacity of the system. If a bridge is very narrow as compared to the highway, then the number of vehicles passing over the bridge will be less, so it will control the capacity of the system. And it is the highest cost per mile of the system. No need for any explanation because it is one of the costliest component in the transportation system. And then if the bridge fails, the system fails because, as you can see in this picture, that basically the bridge connects two cities or two towns across the river, two places across the river. So if the bridge fails, then these two places will be disconnected. The component of a bridge, a bridge consists of basically two components, superstructure and substructure. The superstructure is defined as those structural parts of the bridge which provides the horizontal span, and substructure parts of the bridge which supports the horizontal span. So now you can see the arrow, this horizontal span. Above this bearing, all part of the bridge above this bearing, they are called as superstructure, and all these parts of the bridge below the bearing are called as substructure. So substructure need not to be necessarily below the ground. All those parts of the bridge which supports the horizontal span are called a substructure, and superstructure are structural parts of the bridge which provides the horizontal span. Okay. You can see the abutment of the bridge. Abutment is basically a support system which not only support the load of the bridge, but also support the lateral load from the soil. This is called an abutment. Usually this is a type of, one of the types of retaining walls, but that retaining walls, the typical retaining wall only support the lateral load pressure from the soil, but this type of retaining wall would not only support lateral load from the soil, but will also support the gravity load of the bridge coming from the dead load as well as from the live load or vehicular load. Okay. You can also see a pier. Pier is basically part of the substructure which takes load from the horizontal span or superstructure and transmit it to the pile cap, and from the pile cap it goes to the piles. And bridge deck is usually called as the slab. The slab in the reinforced concrete building system is called as a bridge deck in bridges, and it is actually the surface over which the vehicle runs. This is a bearing plate which is provided beneath the girders in a bridge system and above the piers in order to take care of some vibrations and to avoid crushing of the pier and also of the bridge girders at that location. This is an actual picture from the of a bridge. You can see different parts of the bridge. The bridge deck is actually the surface, as I said earlier, on which the vehicle runs. So this is basically a slab, and you can see a number of girders in this system. There are 1, 2, 3 girders here. Here 1, 2, 3, 4 girders. So these girders are then also joined or connected along the across their width, which is the transverse direction. So in the transverse direction, this connectivity through a beam is done in order to facilitate the distribution of load evenly on the girder, because as you know that when a vehicle passes over a bridge, so some of the wheels of the bridge will be directly coming on one of the girders, so it will load the girder, and all the other girders at that particular instant of time may not be taking any load if these girders are not connected along their widths as shown in this figure, which are called as diaphragm. These are called as bridge diaphragm. This is one reason, and the other reason is that usually the girders provided in a bridge system are very deep, and they are only connected at the top by slab. So in order to connect them also through the depth of the girder, in order to increase their even distribution of the load, and also to avoid any buckling if there is any along the depth of the girders. These diaphragms are usually called as beam diaphragm, and the slab which connects the bridge at the top is called as slab or deck diaphragm. Diaphragm is a term used for a system in structural system for a member. It is used for a member in structural system, which basically helps the distribution of load. So this is in the beam diaphragm, all the girders are connected through the depth of the girders. It will help the distribution of the load and also will avoid any buckling through depth buckling of the girders. Okay, you can also see girders. Girders are shown very clear in this picture, and then from all the girders transfer the load to the pier cap or transom. Transom is basically a member in the structural bridge system, which is a horizontal member on top of the pier. So this is also called pier cap or transom. The pier cap or transom will take the load from the girders and transmit it to the pier. And from the pier, the load will go to the pile cape as shown on the right bottom picture. Okay, pile cage is basically a very thick slab, and then from the pile cape it goes to the piles, and piles then transfer this load to the ground through friction or bearing or both. Types of bridges. Bridges can be classified according to material, such as concrete bridges, steel bridges, or wooden bridges. According to the usage, like pedestrian, only used for pedestrian purpose, highway or railroad. Highway is for vehicles, cars and trucks, and railroad bridges used for rails. Then, according to the spans, also the bridges can be classified as short, medium, or long span bridges. And according to the structural form, like a slab bridge will be a bridge which consists of only a slab without any girders. Then a girder bridge will have girders, a truss bridge, arch bridge, suspension bridge, cable stayed bridges. So many types of bridges according to the different criteria are possible. However, the AASHTO is divided. AASHTO is a code used for bridge design. They have divided classified bridges into three main types, depending on the main structural elements related to the surface on which the user travels. So if main structure on which the vehicle travels is below the deck line, main structure is below the deck line, then it will be called as another one type of system. If main structure is above the deck line, it will be called a different type of bridge, and main structure coinciding with the deck line will be called different types. So basically, the bridges have been divided into three types according to the location of the main structural elements related to the surface on which the user travels. Masonry arches, because the main the surface on which the vehicle runs is now, in this case, the deck system, and the deck is basically above the main structural system which supports the deck. So when the main structural system which supports the deck is below the deck, that are called as arch bridges, truss arch bridges, masonry arch bridges, concrete arch, steel truss arch, and steel duct truss. So all types of truss bridges basically fall in this category, because in arches, the arches are provided below the deck. So as you have seen in the previous slide, that if main structure is below the deck line, main structure is this arch which supports the surface on which the user travels. So when main structure is below the deck line, these are the truss arch bridges, and then whatever trusses are there available, whether they are of concrete, masonry, or any other system, combination of these, they will fall in this category. These are concrete arch bridges, and steel truss arch bridges also falling in this category of bridges. Okay, something about this kind of bridges. You know that with arch shape, gravity loads are transmitted to the supports primarily by axial compressive forces. And at the supports, we have both vertical and horizontal reactions, which must be resisted, and there must be a mechanism at the end of the arches in order to resist these forces. Salient features of arch type bridge. The arch form is intended to reduce bending moments in the superstructure. You know this very well. And the most suitable site for this form of structure is a valley with the arch foundation located on dry rock slopes, which make this an ideal site for arch bridges. And the conventional curved arch rib may have high fabrication and erection cost, although these may be controlled by skilled labor. This is one of the disadvantages, that the conventional arch curved arch bridge will require high fabrication and erection cost. The classic arch form tends to favor concrete as a construction material because concrete is good in compression but weak in tension, and since in most of the arches, in most of the arch forms, concrete will be subjected to compression. So concrete is a favorable material for arch bridges. When main structure is above the deck line, all types of suspension bridges fall in this category. Suspension bridges, and then you have cable stayed bridges and through truss bridges. These are three types of bridges which are included in this category. The suspension bridge is shown in this figure on the left and as well as on the right. Suspension bridge, as you know, or as you might know, it consists of a deck, and the deck is connected through hangers or stringers, and then the stringers are further connected to cables, and cables run through towers, and then they are anchored on both ends to some anchor block. So these are main components of a suspension cable bridge. The suspension cable bridge is very light, and they are very sensitive to aerodynamics. Therefore, they are sometimes provided with stiffener girders on both sides. As you can see, the stiffeners on the right in a close view of this bridge. And also sometimes these decks are tied to the anchor block on both sides of the bridge, as you might have seen in some of the suspension bridges in our hilly northern areas. In order to prevent movement of the bridge in wind, and also some horizontal movements when a vehicle crosses over a bridge, This is another type of bridges where the main system is above the deck line. These are called as cable stayed bridges. The main difference between a cable stayed bridge and suspension bridges, that in suspension bridge there are two cables, main cables running from tower to tower, and then hangers are connected to the cables. The load of the deck is transferred through hangers to the cables and from cables to the anchor blocks. However, in the case of cable stayed bridges, all the cables are radiating from the main tower, and then every cable is taking the load of the bridge. All cables are tied to the bridge, are connected to the bridge, and every cable is taking the load of the bridge and transmitting its part of the load to the tower in this manner. Another type of cable stayed bridge is also shown on the right, where the cables are not radiating with different length, but the same length of the cables are radiating from the tower, and they are taking the load of the bridge. Okay, and this load is then transmitted to the anchor, to the tower. Okay, so in this case, the cables are directly connected to the tower in the bridge, and the load is directly taken by every cable, and every cable transmits this load to the tower, and in turn the tower transmits this load to the pier, and the pier, from the pier it goes down to the ground. This is another type of bridge where the main structure is above the deck line. These are called as through truss bridges. You can see that the trusses are provided above the deck, okay, on both sides of the bridge. On side of the bridge, you can see this is a continuous through truss bridge, and this is simply supported through truss bridges, through truss bridge. The important features of suspension bridges. In a suspension bridge, the flexible cables of a suspension bridge are shaped and supported to transfer major loads to the towers and encouraged by direct tension. The deck is hung from the cable by hangers constructed of high-strength wire ropes and tension. This use of high-strength steel and tension leads to an economical structure. The main cable is stiffened either by a pair of stiffening trusses or by a system of girders at deck level. And this stiffening system serves to control aerodynamic movements and limit local angle changes in the deck. Because these are very lightweight bridges, they are very sensitive to horizontal movements. They must be stiffened to prevent these horizontal movements or to minimize horizontal movement. Cable stayed bridges. As compared to suspension bridges, the cables are straight rather than curved. As a result, the stiffness is greater, and aerodynamic instability has not been found to be a problem in cable stayed bridges. Through truss bridges. A through truss bridge has two main structural advantages. The primary member forces are axial loads because they are part of the truss. And the open web system permits the use of a greater overall depth due to lesser dead load than for an equivalent solid web girder. So basically, these two trusses on both sides of the bridge, they act like an inverted beam, and then the beam is transformed into a truss, an open web truss. Okay, so this is a very economical system. The increased depth also leads to reduced reflection. This is economical for medium spans, and it is aesthetically also pleasing. The last category of bridges are those type of bridges where the main structure coincides with the deck line. Many bridges which exist worldwide fall in this category. They are slab bridges, solid and voided. Also T-beam bridges, I-beam bridges, wide flange beam, concrete box girder, steel box and steel plate girder are parts of this type of bridges. Okay, this is a box girder bridge shown on the left. Girder bridge under construction is shown where there are girders. The girders are basically of steel, but the deck is of concrete. This is a T-beam on the left top. You have a T-beam bridge, T-beam girder bridge, de-stress girder bridge. This is a slab bridge without any girder, and we have multi-cell box girder bridge. This is a multi-cell box girder bridge. So these were different types of bridges. If you have any question, you can ask questions. Otherwise, we will go ahead and discuss loads for bridge design. Okay, if there are no questions, then let's go ahead. The loads to be considered in bridge design can be divided into two broad categories: permanent loads and transient loads. Permanent loads are self-weight of girders and deck, wearing surface, which is the bituminous surface. It is called wearing surface because when vehicle runs on the surface, it gets weared over the years, so it is called a wearing surface. Curbs and parapets and railings, utilities and luminaries, lights, light poles, and pressure from earth retainments, all these are permanent loads. The permanent loads can be then divided into two main categories: dead load of structural components and non-structural attachments, and dead load of wearing surface, DC and DW. They are divided into two components: DC, which is the dead load of all structural components and non-structural attachments, but without wearing surface. Wearing surface has been categorized, has been placed as a different type of dead load. The material properties for pavement, you know that bitumen, the wearing surface will consist of bituminous surface. So you need to know the density of bitumen. The density of bitumen is 140 pound per cubic foot, and of concrete is 150 pound per cubic foot. And different load factors are used for pavement dead loads. Unlike the dead load factors which were used in the design of buildings, beams and columns, the load factors in bridges are different. The maximum load factor for DC type of load is 1.25, and for DW load is 1.5. The reason is that wearing surface will be replaced several times in the lifespan of the bridge. Therefore, the chances of increase in the dead load due to bearing surface are very high. Therefore, a larger load factor is being assigned to bearing surface as compared to load factor of the structural and non-structural components of the bridge. Transient loads are live loads, which basically are coming from vehicular live load, railway, and pedestrian, depending on the type of the bridge. The automobile is one of the most common vehicular live load in the bridges. On most bridges, it is the truck that causes the critical load effects, and it is not every truck that will cause the critical load effect. It will be a special truck, and that special truck is called as design truck, which has been proposed by the code. And then lateral loads, which can be due to water, wind, earthquake, and ship collisions, etc. While considering the design of a bridge, following effects shall also be taken into account, such as impact or dynamic effects. Whenever a vehicle enters a bridge, so it will enter always with some vibration or impact. So these dynamic effects must be taken into account. When a vehicle apply its brakes, so the braking force is due to friction between the tires, and the bridge will also transfer some forces to the bridge. These forces shall also be taken into account in the design of bridges. If a bridge is given in a curve, then the centrifugal forces will also be applying some kind of forces. These shall also be taken into account in the bridge design. And it is also possible that more than one truck simultaneously are present on a bridge, so their simultaneous presence shall also be taken into account in the design of a bridge. The AASHTO, which is the code for the design of bridges, uses basically load models. We have three different loads: a design truck, a design tandem, and design lane. The vehicle combination is described in AASHTO 1994 LRFD, which is load and resistance factor design-based specification. LRFD is basically like strength design method in buildings, because load and resistance factors. Load factors are 1.2 and 1.5 and so on, and resistance factors are factors less than 1, 0.9, 0.85, 0.75, these factors which are applied on the strength. So load and resistance factor design is called, this strength design method is called as LRFD method in bridges. Otherwise, the two approaches are exactly the same. LRFD and strength design methods, though the names are different, approach is the same. And they are LRFD bridge specification are designated HL93 for highway loading, accepted in 1993. It is the design truck of AASHTO, which is called HL93 truck load, is shown in this figure on the left. You can see a truck with three axles. The front axle is having a load of 8 kip. The middle axle is 32 kip, and the rear axle is 32 kip. The distance between the front axle and the middle axle is fixed, which is 14 feet. But the distance between the middle axle and the rear axle is 14 to 30 feet. It has been kept variable in order to model a short as well as a long truck. The distances are between the tires are also shown here. Okay, if we want to apply these axle load in our model, in a one-dimensional bridge model, so they are shown on this line. Simply supported bridge has been modeled as a line element, and three axle loads have been placed on this bridge, with the front axle having a load of 8 kip, middle axle 32 kip, and rear axle also 32 kip. The loads shall be kept in such a manner that they give us maximum effect to be calculated. For example, in the case of maximum bending moment will usually occur at the midspan or near the midspan in a simply supported bridge. So the loads shall be kept such that we get the maximum bending moment, And for maximum shear, as you can imagine, that maximum shear will occur near the supports. So again, the load shall be kept in such a manner on the bridge that maximum shear is obtained. Design tandem is a design tandem consists of basically two axles, and each axle having a load of 24 kip. And design tandem has been included to basically to represent short vehicles, like very short vehicles having very heavy load. For example, one of the short vehicles with heavy load is a tank, army tank, short vehicle but having very heavy load. In Pakistan, we also use our own loads, and one of those loads is a Pakistani tank whose weight is 70 ton, and the 70 ton load is applied in a prescribed manner as defined in the defined by the local authorities, depending on the width and the length of the tank. Usually the tank length is taken as 14 feet, and the load is applied as uniformly distributed load on both sides. Design lane load is a third type of bridge loads defined by AASHTO. The AASHTO design lane loading is like a caravan of trucks. If there are many trucks, one after another, and they pass over a bridge, then in order to simulate this effect, this lane load has been included by AASHTO, which is basically a 0.04 kip per square foot or 64 pound per square foot, and this load is assumed to occupy a region of 10 feet as shown in the figure on the left. But if this load is to be applied on a line element, so this must be multiplied by 10, and this then 0.64 kip per foot shall be applied on this one-dimensional element. In summary, there are three design loads which shall be considered in the design of a bridge: the design truck, design tandem, and the design lane. These loads are superimposed by two ways to yield the live load effects, which are combined with other load effects. Two ways of superposition are truck plus lane and tandem plus lane, whichever is greater. Then we have load modifiers, a factor accounting for ductility, redundancy, and the operational importance of the bridge. This is a type of load factor that we have not used in the design of buildings. This load factor is taken as 1.05 for simply supported bridges and is applied on already factored values of bending moments, as we will see next. Next, we will only discuss now the analysis and design of a simply supported RC slab bridges. So instead of generic discussion, we will be now focusing on the analysis and design of simply supported RC slab bridges. Simply supported reinforced concrete slab bridge is a bridge type which consists of only a slab without any other supporting member such as girders, as shown in this figure. A slab bridge is widely used when the bridge crosses a minor road or small river. Okay. We have designed several slab bridges on the Warsak Michani Road, whose span was around 30 to 35 or 40 feet maximum. Okay, then next is the terminology used in the analysis and design of simply supported RC slab bridges. First of all, what is a design lane? In order to understand design lane, we should understand how the bridges are analyzed. Slab bridges can be analyzed as 3D, 2D, and 1D models, depending on the available tools. If a slab bridge is to be analyzed as 1D model, like line analysis, the bridge width will be divided into various strips. These strips with a strip width E are called design lanes, as shown in this figure. Design lanes are then transformed to line elements 1D model for line analysis. The moments are calculated from line analysis. These moments are then divided by the design lane width to get moment per foot upon the slab bed, like this. This one design width is lumped into a line model, and then loads are applied on this line like this. Truck load, and then the bend moment is calculated from this analysis. And once the bend moment is calculated from the line analysis, this bend moment is again transformed into bending moment per unit width of the slab, like this. So whatever E the design lane width is, these bending moments will be divided by there to give us bending moment per unit. And these design load widths can be calculated using equations as are given in the next slides. There are two types of design lane width. One is for single lane loaded. If a single lane is loaded, then E will be calculated from this equation 10 plus 5 into square root of L1 W1. This E is in inches. L1 is modified span length, which is minimum of S. S is the span length of the bridge, span length. Minimum of S is 60 feet. So for example, let's say if the span length of the bridge is 30 feet, then minimum of S in 60 feet is 30 feet, so L1 will be taken as 30 feet. W1 is modified edge to edge width, the width of the bridge, modified width to edge width. It is taken as minimum of overall width of the bridge are 30 feet. So let's say if overall bridge width is 40 feet, then the minimum is 30 feet, it will be taken as 30 feet. However, if the width is 20 or 30, then it will be taken as 20. So minimum of overall width of the bridge W1 are 30. This will give us E, which is design lane width for single lane loaded case. For a multi-lane loaded case, E is taken is 84 plus 1.44 into square root of L1 W1, and this whole must be less than or equal to W1 divided by NL. L1 is same as single lane loaded, minimum of S and 60 feet, but W1 is now modified for multi-lane loaded, which is different. Minimum of overall width of the bridge at W1 are 60 feet. So if minimum width of the bridge is, let's say, in this case is 40 feet, if width of the bridge is 40 feet or 60, so minimum will be 40, unlike the previous case where it was 30 or 30 feet. And N is the number of design lanes. It is integer means that it will be taken as a whole number. W divided by 12. W is the width of the bridge, and W is 12 is usually taken as the typical design lane width. Okay, so for example, if the width of the bridge is 30 feet, W is 30 feet, so W divided by 12 is 2 point something. So which means that two design lanes can be accommodated at one in the same time. So this factor will be taken as 2, or W1 divided by N will be taken as 2. This will be always rounded down, because if it is 2.8, so third lane cannot be accommodated on this bridge, so it will be always taken rounded down, not rounded up. Okay, these things will be clarified in the example. If you don't understand these things at the moment, it will be further clarified by when we start discussing a design example where these things will be used and clarified. Okay. The design of reinforced concrete slab bridge is done in the following steps. First of all, the depth of the thickness of the slab bridge will be taken from this equation 1.2 into S plus 10 divided by 30, where S is span of the bridge in feet. For example, S is 20, so it will be 20 plus 10, 30. 30 divided by 30 is cancelled in 1.2 feet. So for a 30 feet long slab bridge, the thickness of the bridge will be taken as 1.2 feet. And then for the flexure design of the bridge, 5 Mn, which is the flexure capacity of the bridge, design capacity must be greater than the demand. Mu is equal to 1.05 into 1.25 mdc plus 1.5 mdw plus 1.75 ml plus IM per foot. 1.05 is the load modifier, as was discussed in one of the previous slides. And this is applied over and above all these factors, load factors. Okay, MDC is calculated as DC, which is the self weight of the bridge, multiplied by S square, which is the span length, divided by F because it is simply supported bridge. And WC is H gamma of concrete. MDW is WDW square divided by 8, and this is the wearing surface uh, load and bending moment. And then MLL plus IM, which is the live load bending moment, plus IM means including the impact factor. And impact, in order to include the effect of the impact or vibration, the live loads, which are calculated from tandem or truck, are further amplified by a factor of 33, or which is are further increased by 33%. So the load, the live load from tandem or truck will include some impact or from the vibrations which are produced while a truck or tandem passes over a bridge. So the effect of these vibrations or impact is included indirectly by enhancing the bending moments of the truck or tandem by 33% or 1.33. These bend moments are multiplied by 1.33. And M lane is the design lane movement, which was discussed in the previous slides. Once this MLL plus IM is calculated, the live load, then this will be divided by E, so that this gives us bending moment per unit width. Okay. The slab moments due to live load will be calculated in this manner. First of all, HL93 truck load will be applied on the line element. If we are doing this using one-dimensional element, the maximum moment due to truck load can be obtained by placing the middle axle at the mid span of the bridge and rear axle load at distance of 14 feet. The middle axle load is shown in this figure. As you can imagine that you will have to use several type of different spacing between these loads in order to obtain maximum bending moments. But generally speaking, if you place the middle axle at the midspan of the bridge and the front and rear axle at 14 feet, then generally speaking, you will get the maximum bending moment at the midspan. Similarly, from our tandem, if tandem is kept such that the two loads are placed at a distance of 2 feet from the midspan, then generally speaking, you will get the maximum bending moment, the midspan. Okay, for the maximum bending moment for the lane load is very easy because the load is applied as uniformly distributed load, and 0.64 into S square divided by it will give us maximum bending moment at the midspan. Now, the H2 recommendation. There are different H2 recommendations with regard to the reinforcement, and it says that the main reinforcement, that will be provided along the length of the bridge, span length of the bridge, but the transverse reinforcement along the width of the bridge shall be taken equal to 100 divided by square root of S, or 50% of the main reinforcement, whichever is less, but should not be less than A's shrinkage. And A's shrinkage is 0.0018 into pH, or gross area. Shrinkage and temperature reinforcement in top face of the slab, long and transverse, will be provided. And if we take a typical section of a slab bridge, this will look like this. The main reinforcement is shown with these dots at the bottom of the bridge, because this is a section taken along the width of the bridge, and this is the width of the bridge, and this is the length of the bridge. So if we take a section along the width of the bridge, the main reinforcement will be will look like these dots, which are placed closer to the bottom face in order to take maximum effective depth. And on top of this, the transverse reinforcement is provided, which is calculated from this equation: 100 divided by square root of S, or 50% of AS, whichever is less, but must not be less than minimum shrinkage reinforcement. And on the top face of the slab, shrinkage reinforcement equal to the shrinkage or temperature reinforcement shall be provided both along the long and short, both along this length of the bridge and width of the bridge. This is a video where you will be able to see how the reinforcement is provided in slab bridge. The reinforcement is provided on both the faces of the bridge, along the length as well as along the width. The main reinforcement is bottom reinforcement along the span length of the bridge. Okay. Now next we will discuss a design problem. The statement of the design problem is given on the left. In the figure of the bridge is shown on the right. The statement of the design problem says that we have to design a simply supported slab bridge for HL93 live load. The span length of the bridge is 35 feet, center to center of bearings. Center to center of bearings. Okay, bearing means from the bearing beds. And the width of the bridge from curb to curb is 44 feet. Allow for a future bearing surface of 3-inch thick bituminous overlay. The concrete strength is 4,000 psi and steel is 60 psi. Now look at this bridge on the right. I will amplify this a little bit so that you can see this. This is the bearing. So from the bearing, the span length is 35 feet. Okay. This is the center line of the bridge. Width, the interior width of the bridge from curb to curb is 44 feet. This is the roadway on which the vehicle will run. And the exterior, including this 15-inch curb, is 46.5 feet. Okay. The future bearing surface of 3 inches also included, shall be included in the design. It is the thickness of the slab. Okay, we will start now designing this slab bridge. The span length of the bridge is given as 35 feet center to center. The clear roadway width is 44 feet curb to curb, is shown in the figure. Now for a curb width of 15 inches, total width of the bridge is 44 plus 2 into 15 divided by 12 is 46.5, although it is given in the figure. Minimum thickness of bridge slab is given by formula 1.2 S plus 10 divided by 30. S is 35, 1 plus 1.2. This gives us 1.8 feet or 21.6 inch. So a 22-inch thick slab shall be provided for a span of 35 feet bridge. Okay. With this slab thickness, we will calculate the slab load 22 divided by 12 into 0.15. So it will give us 0.275 kip per square foot. Bearing surface of 3 inch will give us 3 divided by 12 into 0.14. 0.14 kip per cubic foot is the density of bearing surface. So this is 0.035 kip per square foot. And dead load moment, slab moments, WDC is square divided by 8. WDC is 0.275 into 35 square. This is the slab bending moment, 42 foot kip per foot. The bearing surface bending moment is 0.035 into 35 square. It is 5.3 foot kip per foot. Live load moments. Live load moment, as discussed earlier, will be obtained by placing the middle axle in the mid span of the bridge with equal spacing on both sides of this for front and rear axle. So this we can draw shear force and bending moment diagram for this simply supported line element, and this gives us a bending moment of 350 foot kip, which is a bending moment coming from the line analysis. You should note and understand this. For a tandem, we get a bending moment of 372 foot kip, which is greater than the truck load. Lane moment is 0.64 into 35 square. It is 98 foot kip per foot. We will take now. We will take the maximum bending moment. for the two vehicles is coming from for tandem. So we will use tandem bending moments instead of tuck tandem bending moments. And we will also apply 1.33 factor to the tandem bending moments in order to include the effect of vibration or impact. So 1.33 into M tandem is 372 plus M lane is 98. So this gives us 593 foot kip, but for line moments. This must be divided now by E to take to convert this bending moment of the line to two-dimensional in order to include the two-dimensional effects. And for this, we will calculate the single lane loaded E and multi-lane loaded E. The single lane loaded E is 10 plus 5 into L1 W1. L1 is modified span, minimum of S and 60, so minimum is 35. And modified 8 to 8 bit W1 is minimum of W1, which is 46.5 or 30. So we'll use 30. So while when we substitute the values of L1, W1 in this equation, 35 and 30, we get a E value of 172 inch or 14.3 feet. For a multi-lane loaded, repeating the same exercise, we take E is equal to 142 inch, which is 11.84 feet. And as was discussed in the previous slide, that the least of these two E will be taken in our calculation. The least is 11.84 feet, which is coming from the multi-lane loaded equation of E. So now we will divide our bending moment by this E. The bending moment, which is 593, will be divided by 11.84. So this gives us a bending moment of 50 foot per foot. Now we will calculate the amplified bending moments. 1.05 into 1.25 MDC. MDC is the dead load moment. MDW is the wearing surface bending moment, and this is the live load bending moment. 1.75 into 50. This gives us a bending moment of 155.3 foot kip per foot. When we convert this into inch kip per foot, we'll multiply this by 12 and we will get 1863.6 inch kip per foot. Now we can design this very easily. The bending moment is 1863.3 inch kip per foot. And the effective depth of the bridge slab, we know that the total depth is 22 inch. Will provide a cover of 1 inch minus half diameter of the bar which we will use. So let's say we want to use number 8 bar in this bridge. Then the effective depth is bottom cover for slab is taken equal to 1 inch. If the effective depth is, if the bottom cover is taken as 1 inch, then D is equal to 22 minus 1 minus half of 1 inch. This gives us the effective depth of 20.5 inch. AS minimum, we know that it should be 0.0018 into A gross. A gross means 12, which is the unit width, and 22 is the depth of the bridge. So this gives us 0.47 square inch. Our minimum, our reinforcement shall not be less than this. And if we use this hit and trial equation, A is equal to MU divided by 0.9 FYD minus A by 2. With the small a, let's in the beginning we assume 4 inch or 5 inch. Then we can calculate AS for this MU, 1863.6 inch kip per foot. Okay, Fi is 0.9. So after 1 or 2 trials, you will get some reinforcement AS as you have done in the case of building beam design. Finally, we get a area of steel equal to 1.8 square inch. If we want to use number 8 bar, whose area is 0.8 square inch, we will require number 8 bars to be placed at 14 center to center. Distribution reinforcement or bottom transverse reinforcement. According to the H2 5.14.4.1, the amount of bottom reinforcement may be taken as a percentage of the main reinforcement required for positive movement as follows, but not less than shrinkage reinforcement. 100 divided by S. S is 35. 100 divided by square root of 35. It is 16.9% and 50%. So 16.9% is less than 50%, we will use 16.9% because the least value shall be used. And 0.169 of the main reinforcement. Main reinforcement is 1.8. So 0.169 multiplied by 1.8 gives us a value of 0.304 square inch. But then we should compare this value with the minimum reinforcement. And the minimum reinforcement is 0.47 square inch. We will use the minimum reinforcement as transverse bottom reinforcement, which will be placed at 18 center to center if we use number 5 bar. Similarly, the top transverse and longitudinal reinforcement will be also placed according to the H2 code. The maximum spacing for temperature and steel reinforcement in one slab according to this is minimum of this. 110, 18. So also a stop reinforcement in transverse and longitudinal reinforcement will provide number 5 at the rate of 18 center to center, because it is also the minimum reinforcement that we have calculated for bottom transverse reinforcement. So finally, what we will do is that we will provide number 8 at 4 inch center to center is bottom main reinforcement along the span length of the bridge, transverse bottom reinforcement, perpendicular reinforcement to this main reinforcement, number 5 at the rate of 8 inch center to center. Since this is the minimum reinforcement which has been calculated from the shrinkage reinforcement, and according to the AASHTO guidelines, we will also have to provide the shrinkage reinforcement both along the long and transverse direction equal to the shrinkage reinforcement. So this number 5 at the rate of 8 center will provide not only is transverse bottom reinforcement but also a stop transverse and longitudinal reinforcement. Finally, the bridge reinforcement will look like this. This is the number 8 at 4 inch center to center main reinforcement, which is because the section is taken along the width of the bridge. So main reinforcement will look like this: is dots, which has been placed along the length of the bridge. The transverse reinforcement along the width of the bridge is this number 5 at the rate of 18 center to center. Top longitudinal and transverse reinforcement both are placed number 5 at the rate of 18 center to center. These are some bridges. This is one of the longest bridges in the world, which is Grand Bridge in China. This is overall length of the bridge, not span to span, not support to support. The longest span, this is the longest bridge and this is the longest span. Longest span from support to support is in Japan, which is also called a Pearl Bridge or Akashi Kayako Bridge. This is around 2 kilometers. It's a suspension cable bridge. This is the highest bridge in the world, Sidhu River Bridge, 472 meters high. This is a Lansdowne Bridge in Sakar, a very typical example of arch bridges. Jamshoro Bridge, typical example. This is Atak Bridge. This bridge is basically balance cantilever. Basic balance cantilever post-tension multi-box girder bridge. Segmental box girder bridge. This is Malir Bridge, longest bridge in Pakistan. It's 5 kilometers. The new railway bridge, this was constructed in 1877. It's one of the highest bridges in Asia on M2 motorway. This is the end of this lecture. If you have any question, you can ask your questions. Otherwise, the lecture is over. Any question? Any student?